So ln of y minus 1, okay.
Minus ln of 2.
Minus ln of 2.
Yeah. Equals x plus ln of x.
X plus ln of x. Okay.
Solve for y.
And solve for y. Was this complicated for a lot of you? So what I want to do is I can combine all these under one ln, right?
Yes.
How? Division. So this is going to give me ln of y minus 1 over 2. Would you agree with that? It's the same thing?
Yes.
Okay. Now I want to do the same thing over here, but I have a ln here, but not a ln here. Now, remembering what is logarithms? You know, what are logarithms? What's the point of a logarithm? It's an inverse.
Exponent.
So this is a really important idea where I have this this y equals a to the power of x, and then we have some other function here that's an inverse or reflection across the y equals x, and this is y equals what? Log base a. Now these are inverses, so they should undo each other, which means if I take this value and I plug it into here, or I take this value and I plug it into here, I should get what? I should just get x. I should, and y equals x, yeah. I should get y equals x, correct. So I'm going to do that. I'm going to take 1 and I'm going to plug it in. So I have a to the power of log base a of x. That has to equal what? It says I took this and I plugged it in here. It has to equal x because they are inverses. That's the definition of an inverse. They undo each other. And then the next one is a log base a of, and I'm going to take this value and plug it in for x over here. So that gives me an a to the power of x, which has to be what?
X.
Has to be x. This is where logarithms even come from, this idea of an inverse. So this is really, are these equations, are these laws, or are they definitions? Or are they definitions of a logarithm? I'm going to argue they're equations, sure. Are they laws of logarithms, or are they the definition of a logarithm? I think it's the definition of a logarithm. So I'm going to use this idea right here. And I'm going to use this idea to rewrite this x right here. And the point of the reason I'm going to do this is that I want to try to capture everything on this side in one logarithm. Okay, so what can I rewrite this x as? So that I capture under the same logarithm.
Logarithm e or logarithm e.
Jacob Stovard. Okay, yeah, so this is log base e, and so I want log base e of e to the x, right? Would that be right? If I have log base e of e to the x, that's the same idea as this, but this is really what? It's just ln. So I'm going to rewrite that as my ln. So I really have right here, I have ln of e to the x plus ln of x. Are you okay with that? Okay, so this side equals that. So I should be able to put these together. How? Yeah, so I have ln of e to the x times x.
Yes.
Okay, now that I have ln on both sides, consider this idea right here. If I raise both sides by a certain amount, it'll get rid of the ln. Agreed? So what am I raising both sides by? E. So I raise both sides by e, these go away, leaving me with y minus 1 over 2 equals e to the power x times x, correct? What am I supposed to do? What were the directions? Solve for y?
Yeah, solve for y. So
All right. Now what?
you times both sides by 2.
Okay, so I have y minus 1 equals 2 times e to the power of x times, I'm going to move this in the front because it's hard to tell sometimes, is that an exponent or not? So it helps to write it in the front so that there's no confusion. Is that okay? I do that? Right. Now what?
And then you just add 1 to both both sides.
Yeah, we add 1 to both sides. So I have y equals 2 to the power 2 times x times e to the power of x plus 1. Was that a choice?
Yes.
Okay,
Yes.
there you go. There you go. So, yeah, so in the future, if you have a problem, then just write it down, and then let's not use a lot of cost time trying to find it, and we'll just tackle it at the very beginning. Was that Natalie? Where's Natalie? Natalie, was that you that asked if we would cover some stuff at the beginning? So are you good with my response to that? Okay. Okay. This is today is all things to do with trigonometry. And this is going to be a lot of stuff because half of the year last year was trigonometry. There are a few things new that you're going to see, maybe depending on the teacher that you had. But this is 1.6. And this is on trigonometry. Now I want to talk about, so really the definition of trigonometry. What is this? We have this tri here. What do you think that represents? All right, so we're talking about three something. Trigonometry is the study of what? Is the study of triangles. Now there's a really cool relationship that happens when we look at triangles that are similar. Now trigonometry specifically starts with a right triangle, but there's also non-right triangle trig that is incorporated into it as well. Well, let's start with the basic idea of trigonometry. And the idea is that similar triangles are proportionally equal. Now, if I have some angle right here, what kind of measurement is an angle? Is an angle a length? What kind of measurement is an angle? It's a rotation. An angle is a rotation. So I have some rotation there. I have this angle, and I'm going to say that these are similar triangles. We'll say that this is 90 degrees, this is 90 degrees. So we have angle, which indicates that these two triangles are similar. They are proportionally the same. Now I know that because they're proportionally the same, the ratios of the sides will be equal. Now, if I look at this distance here, we'll call this, I don't know, X, and we'll compare it to this one here called Y. And that's another side. And then over here, we'll call this A, and we'll call this one here B. Then there's a relationship that both of these have. X over Y has to equal what? A over B. Yep, because they are proportionally equal. They are proportionally equal. Now, because of these proportions, we know that they're equal. We're going to give them a special name. We're going to call them Bryn of angle A. Well, not Bryn. How about Bentley of angle A? No. How about sine? What if we use sine? What about sine of this angle A? Well, if these have this special relationship, then let's define sine as what? Sine of our angle, let's define it as what? Yeah, let's define it as our opposite over our hypotenuse. So these are just definitions. We could call them Bentley of angle A. We could call them Bryn of angle A, but or Kitty of angle A. But yeah, this is a definition. The definition of sine of angle A is a ratio. Why is that important? Because all similar triangles are proportionally equal. They are proportionally the same. The angles are the same, but the sides are proportionally the same. And then we get this other one that if we have cosine of angle A, then that's of angle, what did I say angle A? What is this called? That is theta. Theta. That is theta. That's my angle. That's my rotation. So cosine of theta is what? Right, but we have a definition for it.
Okay.
Yeah, this is adjacent over hypotenuse. Correct. This is just a definition. It is a ratio because for any theta, for any rotation, it doesn't matter how big the right triangle is, then the adjacent over hypotenuse will always be equal for that theta, for that angle. All right, we also have another one called tangent. Tangent of some angle by definition is a ratio. What is that ratio? Opposite over adjacent. Now, really, I would argue that you really just need to know these. To do all trigonometry, you just need to know these. But then some mathematician decided that to simplify, to make things more simple, we're going to introduce all of the reciprocals as well. So somebody decided that it would be a good idea to have something else that is our hypotenuse over adjacent. Now we have a special name for that. Does anybody know what that is?
Secant.
Yeah, this is secant. This is secant of theta. And then somebody thought it would be a good idea to do the reciprocal of sine of theta. So that would be, let me just zoom out a little bit. Is that too small? Is that good? Somebody else thought it'd be a good idea to do the reciprocal of sine. So we have hypotenuse over opposite, which is what?
Cosecant.
It's cosecant, cosecant of theta. Now I admit, when I first learned about this, when I was it was actually after my master's degree. I didn't learn trigonometry until after I got my first master's degree in special education. I admit that these were confusing to me. I was thinking, how do you really remember which one's the reciprocal? And I think a helpful way to remember this is that the beginning letter will never be the same. Do you see if I did the reciprocal of cosine, if the reciprocal was cosecant, then we have the same letter. We're not going to have the same letter for reciprocals. So for cosine, the reciprocal is secant. For sine, the inverse is cosecant. What is the reciprocal of tangent?
Cotangent.
It is cotangent. It is cotangent of our angle. All right, so all of these are really just, they're called the reciprocal identities. That's what those are called. I would argue you can do all trigonometry without the reciprocal identities. I'm going to make that argument, but there's some things that look really nice and slick if you can write them as the reciprocal. So you have a nice, slick, simplified answer if you can use those reciprocals. You're stealing all my students. Oh, awesome. I didn't recognize you. Thank you. Thank you, Jacob. All right, so let's look at when we first start learning about, what's this called, theta? What kind of measurement is that?
Angle rotation.
It's a rotation. The measurement is a rotation. What is a bigger rotation? A, is that a bigger rotation, or B? They're the same. Both of those have the same rotation. Now, if we talk about it's an angular rotation, the angular rotation is the same. Now, if you're talking about a linear rotation, then B is going to be larger. But when we're just talking about a rotation, the angular rotation, they are the same. So first time we talk about rotation, we introduce the measurement, the units of what? What are the units that we use originally when we talk about rotation? We talk about degrees. We say that this is equivalent to something like 45 degrees. And then we introduce a new idea of radians. So a radian, if you remember, is a radius of a turn. A radian is a radius of a turn. So we have our circle here. Here is my radius right here. And I want to know how many radiuses of a turn a half circle is. So I'm going to zoom in on this. And I'm going to take that length here of 1 radius, and I'm going to measure it here. That's 1 radius of a turn. We'll say right here. And then we have, that's one radius of a turn. And then we have another one. I think I'm making those too big. We'll go back. So here's 1 radius of turn. In other words, a radian. Here's 2, and here's 3, and then there's a little bit left over. So a half circle rotation of 100 degrees is almost 3 radians. Does anybody know exactly how much of a rotation that is, Bryn?
Pi.
It is pi. It turns out to be exactly pi. A half circle rotation, a half circle rotation is pi radians. What does radian mean? It's a radius of a turn. A radian is a radius of a turn. Whatever your radius is, that's how much of a rotation takes place. So what it would be a full rotation? Yeah, we end up getting 2 pi. 2 pi, wrong tool. 2 pi is 360-degree rotation. Yep. So now we have a unit of conversion. I mean, consider if we have that 1 foot equals 12 inches. We have a tool for converting. So if I want to go from feet to inches, I use what tool? I use 1 in the form of, I multiply by 1 because it doesn't change the quantity. I multiply by 1 in the form of 12 over 1.
Wait, no, that's not 1. That's 12.
1 foot. 1 foot equals 12 inches. So we're going to, if I have 1 foot.
Never mind.
Okay. So now what if I want to go backward? What if I want to go from inches to feet? What if I have 12 inches? I'm going to multiply by my conversion of 1 over 12, which will bring me back to feet, right? We can do the same thing when it comes to radians now because we have our conversion. So if I have radians, let's go to the side. If I have radians, and I want to convert to degrees, what is my conversion? Yeah, 180 over pi radians. Yep. So I have something like pi, and I want to convert pi to degrees. I multiply pi by 180 degrees over pi. These cancel out, giving me 180 degrees. That's how it works. So what would be my other conversion going from degrees to radians? Yeah, we could just use pi over 180 degrees to go back to where we started. So just like this idea of conversion shouldn't be different. We have that with, you can do that with anything. We're really multiplying, question? We're really multiplying by 1. This is 1, right? Just like 1 foot or 12 inches over 1 foot, that is 1. We're multiplying by 1 because you can always multiply 1. It doesn't change the quantity. All right, so if I wanted to change something like, so I want to convert 25 degrees to radians. How do I do that?
Multiply pi radians by over 180 degrees.
Okay, so I'm going to take 25 degrees. I'm going to multiply by what again?
Pi radians is 180 degrees.
180 degrees. We can see that the degrees, that unit cancels out. And then we have that 25 over 180, probably can simplify 25. What is it? Sorry?
5 over 36.
Pi over 30. Nice.
5. 5 over 36.
Oh, 5. Okay, 5. 5. 5 pi over 3. Did you just do that in your head?
Yeah.
You're brilliant. Nice work. All right, so that's how we can convert from one to the next. Now I'm going to give you an important warning. I'm not going to say all calculus classes, specifically in this class. Specifically, if otherwise told, we're always going to assume they're radians.
You mean unless?
Thank you. Unless otherwise indicated, we're always going to say, we're always assuming they are radians. So, in fact, I can't think of any problems that I've seen so far, and that this is my 3rd year teaching calculus, and I can't think of any problems on the AP test that were in degrees. They're all in radians. So this is a really important idea. So you won't have to convert. You might on the homework, you might have to convert, but when you're, as far as the AP test and when we get into calculus, everything is going to be in radians. So we really need to be able to wrap our heads around what that means, radians. Now here's another important idea that we need to wrap our heads around. When it comes to, let's look at, compare a unit circle with sine and cosine, right? Here's sine of theta. And I'm going to go ahead and construct a right triangle here. And we're going to call this the unit circle. Unit circle. Does anybody remember what a unit circle is?
Yeah.
A radius of 1, and it's centered at the origin. It's centered at the origin. Those are the two conditions of a unit circle. It has a radius of 1 and it's centered at the origin. So we have some point here that has an x and a y assigned to them. And I want to, and then I have a theta right here. And if I consider what sine is, what is sine in this case? Sine of theta would be what? Yeah, so this is my x. I have so many spaces to the right, left, and then so many spaces up or down. So I have, so this, it's going to give me what again?
Y over 1.
Y over 1, which is just y. So for a unit circle, sine of theta equals what?
Y.
What about cosine of theta? X over 1, which can be simplified to? X. We're doing adjacent over hypotenuse. That gives us x over 1, which is just x. So we need to remember that cosine of theta for a unit circle equals x. That becomes really helpful to think of our x value. This is just for a unit circle, right? If we had something with a circle of a radius of, I don't know, 3, how does that change my cosine of theta versus my sine of theta? If this is still the origin, this is still 0, 0. Bentley.
The cosine would be x over 3 and the sine would be y over 3.
How about we just multiply it by 3? What used to be a unit circle here has now grown by a factor of what?
3.
So each of the x and y value also grew by a factor of 3. Does that make sense? That we're multiplying by 3. So that's the only thing that changes when if you're not dealing with a unit circle, I don't know if you even need, I don't think you even need to know that, but that's just interesting. I don't think you need to know that for calculus. But yeah, just if anything, if the unit circle has grown to have a radius of 2 or 3, then everything has grown by a factor of that amount, whatever the radius is. So let's make sure that we stay on track. Our x is our cosine, and our y is our Sine for a unit circle, yep. Now let's consider special angles. Special angles. Now, because in this class, radians we're almost exclusively radians. I'm going to actually say exclusively, other than today's homework, right? I'm pretty sure everything will be on the homework will be exclusively radians. We're going to do our special angles in radians. What is one of our special angles? One special angle looks like, well, all right, well, all of these are going to be right. All right, 45 is one of our special angles, correct? 45. 90 is also a special angle too, I have to admit. So this is our 45, 90 triangle. What's our other special angle? 30 is another special angle, and 60 is another special angle. Now, because we are using radians, I'm going to change this. What is 45 degrees in radians? Pi fourths. Now, if you think of a circle, you divide it up 45 degrees. These are 45 degrees here. And so we're taking pi and dividing it into how many slices? 4. So that's going to be, it's going to be pi. Each one is going to be pi fourths. To go around the circle, that's pi fourths plus pi fourths plus pi fourths plus pi fourths, which will give you 4 pi fourths, which is pi. So this is pi fourths. Is everybody comfortable with how I got pi fourths? Okay, a half circle is how many, well, what is that in radians?
Pi.
It's pi, right? Now, if I take this, if I divide up this into, it's also 180 degrees, right? Now, if I take 180 degrees and I cut it in half, then these are 90 degrees, right? Now, if I take 90 degrees and cut them in half, what do I get? If I take 90 degrees and cut it in half, I get 45. So I'm going to cut that and cut that. This is 45, and this is 45 degrees. This is 45 degrees. This is 45 degrees. Now, so one of these rotations is 1 out of how many? 4. So I have 1/4 pi's. This is 1/4 pi. This is also 1/4 pi. This is also 1/4 pi. And this is also 1/4 pi, because 1/4 pi plus 1/4 pi plus 1/4 pi plus 1/4 pi equals what? It equals pi. Now we just write it, instead of 1/4 pi, we just write it as pi fourths. Are we good with that? Okay. Now what about a 30 degree? If I have this pi, how many slices do I divide up a 30 degree? How many times does 30 go into 180 degrees? 6. So this becomes how much in radians? Pi over 6. Do you want me to explain this? Is everybody good with that? Yes, no, maybe so? Okay. This is 60 degrees right here. That's 60 degrees. If I have a half circle of 180 degrees, how many 60 degrees are in 180 degrees? 3. So how many, so each 60 degrees is what in radians? Pi thirds. Yeah, pi over 3 or pi thirds. So this is my pi thirds. Pi thirds, good. Now what's really, so these are unit circles. So both the hypotenuse has to be 1 for both of those. And then I'm trying to figure out what this length right here is. What's that length? How do I calculate that? Using that starts with a P. The Pythagorean theorem. So using the Pythagorean theorem, I have x squared plus x squared equals 1 squared. And then I combine these together to get 2x squared equals 1. Then I divide both sides by 2 to get x squared equals 1/2. And then I take the square root to get the square root of 1/2, or the square root of 1 over the square root of 2, or 1 over the square root of 2. Square root in the denominator is never considered simplified, so I'm going to multiply by the square root of 2 over the square root of 2, which gives me the square root of 2 over 2. Okay, so this length right here is what?
Square root of 2 over 2.
The square root of 2 over 2. What length is this?
Square root of 2 over 2.
Square root of 2 over 2. So sine of pi fourths is what? Yeah, it's opposite over the hypotenuse, which is going to give me the square root of 2 over 2. What is cosine of pi fourths?
Square root of 2 over 2 over 1 is square root of 2.
Yeah, square root of 2 over 2 over 1, which is the square root of 2 over 2. Yep, we're getting that's the adjacent over hypotenuse. So that's also giving me the square root of 2 over 2. Is everybody following? Okay. We're going to do the same thing over here with our 30, 60, 90 triangle. Now, there's something really cool about all 30, 60, 90 triangles. It has something to do with the longest side and the shortest side. What relationship, I'm just going to go to the top, I guess. Am I going too fast? Are you still copying? Are you still copying? Jacob, you good? Awesome. Okay. There's a cool relationship between the longest side and the shortest side of all 30, 60, 90 triangles. What is it? The longest side is double the shortest side. So if the longest side is, oops, wrong tool. If the longest side is 1, the shortest side has to be what?
1/2.
1/2. So this is 1/2. Now I want to figure out this length over here. And so I'm going to use the Pythagorean theorem again. So a squared plus b squared equals c squared. I have x squared plus 1/2 squared equals 1 squared. Did I do that right?
Yes.
And then we have x squared equals 1/2 squared is 1/4. Oh, that's plus, not equals. Equals 1. And then I subtract 1/4 from both sides. So that gives me x squared equals 1 minus 1/4 gives us 3/4. And then we take the square root of both sides. That gives me the square root of 3 over the square root of 4. What's the square root of 4?
2.
So I have the square root of 3 over 2. So this length over here is the square root of 3 over 2. What is sine of pi 6? It's opposite. Here's my pi 6. It's the opposite over hypotenuse. Here's 1/2. What is cosine of pi 6?
Square root of 3 over 2 over 1 is square root of 3 over 2.
It's the adjacent over hypotenuse. That's the square root of 3 over 2. What is sine of pi thirds? Opposite over hypotenuse, which is
Square root of 3 over 2 over 1.
square root of 3 over 2. And then cosine of pi thirds,
1/2.
it's 1/2. It's my adjacent over hypotenuse. That is 1/2. Now, what's really cool is you can memorize all of this, or you can recreate it on a test so you know what they are, or we have a cool hand trick. Bryn, do you like my hand trick?
You already have a diagram of it.
Do you want me?
Yes, you do that all the way. It's in the upper right hand corner.
All right, I'm gonna use that. I actually think it's, yeah,
You left it there on purpose, I'm pretty sure.
I did. All right, so, but it's not, we can't use degrees.
Well, you can drag over it once it's.
Well, help me out. Well, let me make this darker.
Copy it and then.
Well, you have,
Sure. Yeah, let's copy it like Bryn said. Let's copy it. Let's drag it back over here.
you already have the answer for it.
Let's go back up here. Okay. I'm sorry, Bentley, what'd you say?
You already have the answer to 3 of the 5, right?
And right, yeah. So let's just translate this back over. So what is 30 degrees? That is pi over 6. So that doesn't look like a 6. How about that? Is that better? Maybe not. Pi over, come on. There we go. All right, what is 45 degrees in radians?
Pi over 4.
All right, pi over 4. What is 60 degrees in radians?
Pi over 3.
Pi over 3. What is 90 degrees in radians?
Pi over 2.
It's pi, it's, what is it? Okay, pi halves. Yep, pi halves. So I get pi halves. What is 0 degrees in radians?
2 pi ampere radians.
And you have both. All right, so let's use our hand trick. Do you see how we have the first quadrant here? Does everybody see that we have the first quadrant?
Yes.
Okay, so if you think about it, this is 0 degrees. We always need to think when conceptually in trigonometry, we think of our if our terminal side and our initial side are the same, it means we haven't rotated at all. So the positive x-axis is the initial side. If we rotate counterclockwise, positive or negative? Are the angles positive or negative?
Positive.
Positive. If we rotate clockwise, it is?
Negative.
Yeah, we have negative angles. So this looks like a rotation here of pi 6. This is a rotation here of pi 4ths. This is a rotation here of pi 3rds, and this is a rotation of pi halves. So we can do this on our hands anytime we would like. So using your hand, what is sine of pi 4ths? What finger do you put down? You put the middle finger down. From the sine direction, how many fingers do you have up? Okay, so here's our formula here. We have the square root of 2 over 2. That's the answer. Let's do another one. Let's go backward. Let's get rid of all my lines here. Okay, this turns out to be the square root of 2 over 2, right? All right, what is cosine of pi 3rds? What finger do I put down? What's that finger called? It's called your index finger. Sure, we point with it, but it's called our index finger. So I'm going to put down the index finger. From the cosine direction, how many fingers do I have up? 1. So that's going to give me the square root of 1 over 2. The square root of 1 is 1. So I get 1/2. So I get 1/2. What is sine of pi 6? So we're going to put down what finger? We call it the ring finger. Put down the ring finger. How many fingers do you have up on the sine direction?
1.
1. So I have the square root of 1, which is
1.
over 2. So we have 1/2. So that becomes 1/2. What if I have cosine of pi halves? What is cosine of pi halves? What finger do I put down?
You would put down your thumb, 0.
Okay. So I have 0 fingers from that side. So I do the square root of 0 over 2, which is 0. Yep. What is sine of pi halves? What is sine of pi halves?
That is 1. If you have 4 fingers up.
You have 4 fingers from the sine direction. Put 4 into the square root. Square root of 4 is?
2.
2 divided by 2?
Oh, 1.
1. Yep. So we get 1. Does everybody understand how to use the hand trick? If you are confused, where can you go as a resource to learn the hand trick? Canvas. I have it on Canvas. I think it's that important that I have it on Canvas. So you have if you're not sure how to do this, go back to Canvas and watch the video on how to do the hand trick. Is everybody good with the hand trick? Can we move on? Okay. So I would love to spend some time doing all of the unit circle. In fact, I think it is worthwhile. I am concerned about the last piece of class that I don't want to miss talking about, and that's transformations. So I'll just do a couple then. If this point right here is what? If this is a unit circle centered where? Where is it centered?
Origin.
The origin. What's the radius?
1.
1. What is this coordinates? It has an X and a Y associated with it. What are they?
Square root of 2 over 2.
Yeah, it is the square root of 2 over 2, comma,
Square root of 2 over 2.
the square root of 2 over 2. Where did I get that?
Unit circle.
The unit circle. What is my x value in regards to trigonometry?
Cosine.
That's my cosine. That's my cosine. That's my cosine of this angle right here. What is my y value?
Sine.
It's my sine. It's my sine of that rotation of that angle. All right, let's compare that to some other point. What if I have for my unit circle, what would this point here be?
Bring that like negative square root of 2 over 2, and then just square root 2 over 2.
Why is this negative?
On the negative x.
Yeah, if we go over here, this is my negative. This takes me further into the negative for my x value. This takes me into the positives for my x value. I should actually make that positive. Positive. And so my x value is negative. And so because so the cosine is also negative in the second quadrant. How do you identify the quadrants? This here is quadrant what?
1.
1. And then which direction do you go when you count to 2 and 3 and 4?
Counterclockwise.
Counterclockwise. This quadrant is what?
Second.
That's our second quadrant. What quadrant is this?
Third.
Our third quadrant. What quadrant is this?
Fourth.
Our fourth quadrant. Where's the fifth quadrant?
Nowhere.
There's nowhere. Yeah, this is two-dimensional. So what about this point right here? Assuming that we're rotating in increments of pi 45 degrees. So that means, wait, I do want to talk about this rotation. What would this rotation here be then? In radians. What's that rotation in radians? One of these is what?
Pi fourths.
Pi fourths. So this is how many?
3 pi fourths.
3 pi fourths. That is 3 pi fourths. So I want to know what sine of 3 pi fourths, what that is.
Square root of 2 over 2.
It's the square root of 2 over 2. It's my y value. What is cosine of 3 pi fourths?
Negative square root of 2.
It's negative the square root of 3 over 2. Nice. Bentley, good job. Negative the square root of 2 over 2. What is this point here in the the third quadrant? Yeah, 5, what is it? Oh, you're talking about the rotation. The rotation is going to be 5 pi fourths. I agree with you. So the rotation, so my angle, it would be sine of 5 pi fourths versus cosine of 5 pi fourths. But what is the point? What's this x and y value? Yeah, these are going to be negative. We have negative the square root of 2 over 2, comma, negative the square root of 2 over 2. Why are they both negative?
Because they're both negative.
We go deeper in the side in the third quadrant, we go deeper into the negative x value. We go deeper into the negative y value. So both of them are negative. So the rotation, somebody said it already. Why is this a rotation of 5 pi fourths? Each rotation is how much? 1 pi fourths. So we have 1 pi fourths, 2 pi fourths, 3 pi fourths, 4 pi fourths, 5 pi fourths. We have 5 pi fourths. What is cosine of 5 pi fourths? Negative square root of 2 over 2. What is sine of 5 pi fourths? It's the same thing. What about over here? What's this point right here?
Square root of 2 over 2 is negative square root of 2.
And then negative the square root of 2 over 2?
Yes.
Okay, why is this negative?
Because the y is negative on the x positive.
Yeah, in the fourth quadrant, x is positive, the y is negative. So we would be, what's the rotation? What's the rotation to get to this point?
7 pi fourths radians.
7 pi fourths radians. So I have cosine of 7 pi fourths is what?
Square root of 2 over 2.
What is sine of 7 pi fourths?
Negative square root of 2 over 2.
Negative square root of 2 over 2. Okay, so we've done a ton of stuff. All this stuff is really important stuff with trigonometry. You have the hand trick to help you. Of course, you could just use you could use the Pythagorean theorem to calculate everything over again. But I think it's helpful to use the hand trick. It's a quick way to get that information. Now, I'm not going to get into all of the other stuff, but we should be able to figure out pi 6 as well, right? Or pi thirds. We've already calculated. What is this point right here? What's this point here?
Square root of 3 over 2.
As a square root of 3 over 2, comma,
1/2.
1/2, which means that this point over here, which has the same height as the other side and the same adjacent side, has to be what?
Negative square root of 2.
This point here is negative the square root of 3 over 2, comma, 1/2. Now, what's that? Use the hand trick. Okay, so this is so I want to recreate, this is is that my sine or my cosine?
Cosine.
That's my cosine. X is cosine, right? Yes, no, maybe so? X is cosine. Cosine, is that from the pinky or the thumb direction? It's from the thumb direction. What finger do I put down to recreate the square root of 3 over 2? I put the ring finger down. Do you see how I have 3 fingers up now? What's that? How did I'm trying to show you. Oh, how did I get the square root of 3 over 2? All right, so what rotation is this? We divided the circle up into how many slices? So that's it's pi 6, right? It's pi 6. So I have pi, so that's my cosine. So I'm trying to figure out cosine of pi 6. What finger do I put down? What's my pi 6 finger?
Ring finger.
Cosine is from pinky or thumb? Thumb. How many fingers do I have up? 3. Remember our formula is the square root of x over 2? X is 3. So it's the square root of 3 over 2. Now you can certainly, Natalie, one possibility is you can always recreate these. You can recreate these by using I don't actually even remember where we were, right here. We can recreate these values for our special angles by using the Pythagorean theorem. Or you can use the hand trick. I suggest the hand trick. It's a great way of getting that information really quick. If you're not sure how to use the hand trick, where's the resource to get it?
On Canvas.
On Canvas. It's on Canvas. It's one of the videos on Canvas. Watch the video on Canvas. All right. So where were we? Here we are. Okay. So then what is this point right here? 1/2 square root of 3 over 2. This is, how much of a rotation is this?
Pi thirds.
Pi thirds. So we can use the hand trick to figure out cosine of pi thirds and sine of pi thirds to get those values. What does this point here have to be?
Negative 1/2 on square root of 3.
Negative 1/2, comma, the square root of 3 over 2, which means that this value here has to be
Negative 1/2, comma, negative square root of 3
negative 1/2, comma, negative the square root of 3
over 2.
over 2. This is just the unit circle, and you should be able to figure out all of these by using your hand trick. By using your hand trick, and you can always figure out, this is the most helpful thing that I can think of. If I have this rotation, let's say we have this. I know that this is pi 6. This rotation here is pi 6. Now I want to figure out what point is right here. Now what I could do is what does this have to be?
Pi 6.
Yeah, that has to be 5 by 6. Yeah, it has to be 5 by 6. So we're trying to figure out then for this, is that my x or my y value?
X.
My x, is that sine or cosine?
Cosine.
So whatever goes in here is my cosine of 5 pi 6. And what goes in here? sine of 5 pi 6. Yep, 5 pi 6. I don't know. So you should be able to figure out all these. A lot of times we use an acronym of all students take calculus. All stands for all of our trigonometric ratios are positive in the first quadrant. S stands for sine. Only sine is positive in the second quadrant. T stands for what? Only tangent is positive in the third quadrant. How is tangent positive in the third quadrant if sine and cosine are both negative?
Because because negative number divided by negative number.
What is tangent of theta in terms of sine and cosine?
It's sine divided by cosine.
It's sine of theta divided by cosine of theta. We have a negative divided by a negative, which is a positive. Only tangent is positive in the third quadrant. What does the C stand for?
Cosine.
Cosine. Only cosine is positive in the fourth quadrant. Only cosine is positive in the third quadrant. I don't use this acronym. I just think in my head is X positive, is Y positive or negative? That's how I think of it. I don't think of all students take calculus, but you can certainly remember it that way if you would like. That's up to you. All right, I feel like I've covered all the important stuff. I still need to talk about transformations. Does anybody have any questions about all of the trigonometry? Trigonometry was so huge last year. Half of the year, almost half of the year was trigonometry last year. If you recall all the stuff you learned last year, do you remember that a large portion of last year was trigonometry? Adam, what do you think? Sure, you're just saying that? You don't remember? Vaguely? Okay, all right, fair enough. Fair enough. The whole summer went by too, so fair enough. Bryn, do you remember that a lot of last year was trigonometry?
Yeah,
Are you just saying that?
a lot of last year was trigonometry.
Yeah, a lot of last year was trigonometry. Yeah, it turns out about
Trigonometry and logarithm.
Yeah, turns out about half of the year was a little less than half of the year is trigonometry. All right, so one last thing we're going to talk about transformations. Transformation, going to zoom in on this, zoom in transformations. I know I'm covering so much stuff. So if you are not familiar with these things, then it just means you're going to have to do more study. Doesn't mean it's impossible. It just means more study. We are going to be doing right now, we're doing transformations. Transformations. What does y equals sine of x look like? Don't say, don't say, don't say, don't say. Let's consider these values. Let's say that this is pi fourths. This is pi halves. This is 3 pi fourths. And this is pi, this would be pi. When I plug in pi fourths into this, actually, let's plug in pi halves. Actually, let's even go back even further. Let's plug in 0. If I plug in 0, what do I get?
0.
I get 0. What if I plug in pi halves? I get 1. What if I plug in pi?
0.
I get 0. So there's something that happens, and in fact, what is sine of pi fourths? What? Yeah, the square root of 2 over 2. So we're going to get something in between, in the middle somewhere. In fact, we have a graph that looks something like this. And in fact, what this turns out to be is periodic. It ends up repeating itself. As we go around and around the circle, once you've made a full rotation, you can keep on going to more rotations. Then this repeats itself over and over and over again. This is called a periodic function because it repeats itself. What does cosine look like? What does cosine look like? Let's plug in 0. What do we get when we plug in 0?
1.
We get 1. So I'm going to start up here at 1. What happens when I plug in pi?
1.
Isn't that just the opposite of sine?
What do you mean by opposite? Opposite, it's hard to say the word opposite in math because
That's what I was
do you mean the reciprocal? Do you mean the inverse? So we're going, what happens when I plug in pi?
-1.
I get -1. So I get a value that's down here at -1. So at pi, that's this rotation here. What's my x value when I rotate a half circle?
-1.
It's -1. So that means that my cosine of pi is -1. So I get this -1 right here. So we get something like this. We get something like this. And this is also periodic. So we repeat ourselves as we go around and around the circle. This repeats itself over and over again. And we get something like this. How are sine and cosine different?
They start in a different place.
Yeah, we start at a different place. One, we start at 1 when x is 0, y is 1. And the other one, we start at 0, 0. What about tangent? We talked about what tangent was as a ratio. I hear a lot of talking. Does somebody have a question? Do you guys have a question about math? Do you guys have a question about your social life? You have a question about something that's not math? Do you have a question about math? Why are you guys talking? Nobody wants to answer. Yeah. Okay. I just want you to focus because I am concerned when I hear students, when I get emails from parents or students saying, Mr. Hall, I just, I don't understand calculus. We haven't started calculus. We haven't even started calculus. So I want you guys to pay attention so you are learning in this class. If you're asking a question about class, then certainly ask another student. That's fine. I don't mind being interrupted if you're asking a question about math, but let's focus on math. We talked about the ratio that represents tangent. Does anybody know what that is? Yeah, it's sine of x over cosine of x. Here's sort of a proof for you. Here's a proof for you. If this is theta, and this from theta, this is my opposite side. This is my hypotenuse. And this is my adjacent. Here's my proof. Then tangent of theta equals what?
opposite over adjacent.
Opposite over adjacent, good. Now we're saying the claim we're making is that tangent of theta equals sine of theta over cosine of theta. What is sine of theta?
Hypotenuse over opposite.
Sine?
Opposite over hypotenuse.
Opposite over hypotenuse. What is cosine?
Adjacent over hypotenuse.
When we divide by fractions, here's a tip.
Yeah.
Okay, we keep opposite over hypotenuse. We change from divide to multiply and we flip. When we simplify, cross simplification, does that give us the same thing?
Yes.
Yep. So tangent of theta equals what ratio?
Sine over cosine.
Sine over cosine. Tangent of theta equals sine over cosine. Well, what if sine is what? X or Y for a unit circle?
Y.
Y. So we're saying that tangent of theta equals Y over what?
X.
Crazy. Crazy stuff. Crazy stuff. Okay, let's go back up to here. All right, so something, if I'm going to graph this, y equals tangent of x, there has to be some values that are not allowed. What are some values of tangent that are not allowed?
X equals 0.
X, yeah, the denominator can't be 0. So what's an angle that would give me cosine of that angle would be 0, which would be undefined.
I have.
Pi halves. Remember our hand trick? If we have pi halves, so we have from our cosine direction, we're going to put this finger down here. That is our pi halves finger. So am I doing that right? Is that backwards? I don't know if that maybe is back. Yeah, I think that's right. Okay. So I'm going to put this finger down. I have 0, square root of 0 over 2. That is pi halves. So anytime I have pi halves, that should not be allowed. Pi halves and negative pi halves. And then we repeat ourselves. If you consider how often when we rotate, when is cosine seems to have a period of pi because it's tangent does. Tangent is positive in the first quadrant and the third quadrant. So tangent has a period of pi. So this repeats itself again for, pi more. So pi and pi halves, which would be, 3 pi halves? What would be the next one? 5 pi halves, 5 pi halves, 5 pi halves. So there's something interesting happening here. In fact, we have what's called a vertical asymptote. We have these vertical asymptotes that go in here where the denominator for cosine would be 0. And so our graph is going to look something like this. And because it's periodic, it repeats itself over and over again to infinity. That is for tangent of x. We're missing 3 more trigonometric functions. What are they?
Cosecant, secant, and
Yeah, secant, cosecant, and cotangent. I'm going to give you a second, and then I'm going to show you. Let's do cosecant next. What is cosecant? It's the reciprocal identity for what? Cosecant is the reciprocal identity for what?
sine.
For sine. Remember that the first letter has to be different. So sine, we should not confuse sine, or we should not confuse secant for the reciprocal for sine, because those would give you the same letter. We should not confuse cosecant for the reciprocal of cosine, because they have the same letter, the beginning letter. So let's not confuse those. All right, are we good? Yes, no, maybe so? Okay. Now I'm going to we're going to do cosecant first. So I'm going to grab our cosine right here because there's a really cool relationship that they have. And they should have a cool relationship because they're just the reciprocals of each other. So I want to graph, let's zoom in on this. I want to graph our y equals cosecant of x. Now cosecant is a reciprocal, so I could rewrite this as what? 1 over what?
Cosine is the sine of x.
Over sine of x. Now we have a fraction again, which means that the denominator can never be 0. What are some values for the denominator, for x, that would give me a 0 in the denominator?
0 over units, 45.
Yes, so well, isn't this a 0?
It is.
And this would be a 0?
Yes.
And then you said where else?
2 pi.
2 pi. So way over here at 2 pi. We can't have those values. So we end up having vertical asymptotes again. We have a vertical asymptote here. We have a vertical asymptote here. We have a vertical asymptote here that we converge on. The graph, let me finish this. So this is sine right here, right? This is sine, right? Sine, that's sine. Now I'm going to graph cosecant. There's a really cool relationship. What is an asymptote? An asymptote is what? It can't be crossed, but we also, convergence is actually even a bigger part. Actually, it can cross a horizontal asymptote in the middle. When we're talking about horizontal asymptotes specifically, we're talking about end behaviors. I can give you an example where it would cross in the middle but we're looking at end behaviors, okay? So we're talking about convergence. Convergence is an important word when we're talking about asymptotes. So we have to converge. Now, if I have some value here, let's call it pi. What if I put pi halves in here? What's pi halves here? So sine of pi halves is what?
1.
1. So that would give me what here?
1.
1 over 1. So I get this point right here. When x is pi, I get that point there. I have to have convergence. So we converge on these lines. What about when x is 3 pi halves? You get -1. So we have this point here, which means we have convergence by the definition of an asymptote. We have to have convergence. What do you think is happening over here?
-1.
Which means it's going to converge downward, right? It's going to be concave down. What about over here? Concave up. Yeah, so we should have something like this. Knowing this information, any guesses on how to do secant of x? Which graph should I grab for secant? Cosine. Let's go grab cosine. Where's my cosine? What did I do with cosine? I don't know where it is. I'll have to zoom out. We have cosine. Oh, here it is over here. Let's zoom in a little bit. Go over here. Grab this one, copy. Go further over here. Paste. Knowing what we know about cosecant. Cosecant. So this is going to be the graph for what? What function am I going to graph now?
Secant.
Yeah, secant. So knowing what we know about cosecant, how do we graph secant?
At every place where cosine reaches 0 on the x-axis, then vertical asymptote.
Nice. We have vertical asymptote there. We have vertical asymptote here. 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 What's happening in here? Concave up or concave down? We'd have concave up. We would have something concavity, the graph of understanding and interpreting the concavity of a graph is really important in calculus. So when we use the word concave, I'm talking about that like cave area here. We're talking about concave up or concave down. We do not use the word convex in calculus. We say it's concave up or concave down. What is happening over here? Concave down. We're going to get something that looks like this. What about over here? Concave up. We get something like this. What about over here? Concave down. Now, what about all of the transformations for these? What if I wanted to take this secant of x, and I wanted this graph here that has all these, these little u's all over the place, and I wanted to shift it upward. How would I do that?
You would add to the function.
Yeah, we had, in fact, let me write it. Let me go to Desmos. Is everybody done with this?
No.
Is Mr. Hall going too fast? I hate when Mr. Hall gets excited in calculus because he talks way too fast. I can't keep up. Sounds like a bunch of Greek that he's spewing out. Now, calculus is really cool. We just haven't started calculus yet. Okay, are we good now? Yes, no, maybe so? Okay. So I'm going to go over to Desmos. These transformations are super, super important. So let's do Desmos. And let's do, I wonder if Mr. Hall lied to us. What if he graphs secant of x and he's completely wrong? Huh, I don't think he was wrong. So we have this crazy graph here. When does it stop going left and right?
Never.
Never. These are periodic functions. They repeat themselves over and over and over again. Now I want to take this graph and I want to make it go upwards. This point right here of 0, 1, I want to make it go all the way up to 0, 4. How do I do that?
You add 3 to the function.
Do I add 3?
3. Yeah.
Okay. Are you sure? Okay, let's do it.
I
Yep.
could be wrong, but
So we want it to go up 3 units, right? We want it to go from here to here to here. So 3 units. So you're right. So in the function or to the function?
To the function.
To the function. This is vertical. So we add 1, 2, 3, 3 points to it and it goes up. What if I want this to go right?
you would subtract to the function.
Yeah, we have that funny business. We do something in the function. We subtract. If I want to go right, it's the funny business. Bryn, you completely changed my description of transformations. And you're going to hear it again. Okay, minus 1, 2, 3, 4, 5, 6. You see that we're moving to the right? What if I want to squish this graph? I want to do a vertical stretch by a factor of 2.
You multiply 2 to the function.
Multiply 2 to the function. Here's multiply 1, nothing changes. That's the cool thing about multiplying by 1. Then we multiply by 2 or 3 or 4 or 5 or 6. Actually, everything's being stretched up. Everything, including this point, is being stretched up. All y values are being stretched up by a factor of 6 in this case. Okay, everything, all points are being stretched up by that factor. All right, what if I want to flip this graph? I want to do a vertical flip.
Make it negative.
I make it negative. I make where negative? In the function or to the function?
To the function.
To the function. To the function, we look at, there is a vertical flip. Vertical flip. If I do a horizontal flip, nothing changes. What does that say about the function? Odd or even? It is even. If the function is equal to the function minus x or negative x, then it is even. Good job. Nice. All right. I think I covered all this stuff. That was a lot of stuff. I get it. There was a lot of stuff that we covered, but a lot of important stuff. Negative secant of x, like this. It looks like it's shifting. It's actually doing a vertical flip.
Because
It's-
it's symmetrical, it's just.
Yeah. It looks like a shift. It's actually a flip. It's a vertical flip. Yep. Yep.